So previously we were finished with this logistic regression and we are still in the same CLO, but I revised it again because at least we can say that this logistic regression is finished. And now we are going to start the neural network and then we will go with the decision trees and then it will end. Okay. So neural network you already have studied in your previous course. What is that one? So normally I will not talk about the neurons that we have. Some slide will come, but I will skip that speedily. The neurons eh, which we have as a human. So we all know. So I will not go into that detail. But so in computer science, neural network is some unit, some small component which will take inputs into the form of vector or array. I I already told you you can, if somebody is not understanding vector, he can take something an array in his mind. So neural network is what? It is small component or unit which will take some vector and it will give you, it can be single output, it can be multiple outputs, but here in the sentence it is mentioned single output, okay, because it is talking about one small unit, so that's why. So that is the reason. So again, it is what? It is a small unit which will take vector and it vector of values. It can be any values. And those values would be numbers, okay? Those, if your data set is not in numbers, then you have to convert it into numbers. That's why you were, uh, when we were doing how to prepare the data, then there was some topic in it, how to convert your data into numeric form. There was some topic there. And we converted some nominal data, which were nouns, into numeric form, and then we can use it. So, and it will produce what? Single output. So the mathematics of this neural networks is very much similar to the logistic regression. Whatever you have studied in logistic regression, that is same concept is applicable in neural network. That's why I was saying when we were studying logistic regression, at that point, I was saying that logistic regression is the part of neural network. That was the reason. That was the reason. The same probability formula, but in logistic regression, we have the sigmoid function. Here, you can use softmax, okay? You can use softmax. Even you with the neural network, if you are going to do the binary classification, then you can use sigmoid, okay? But if you want to predict more than one classes, then you can use softmax, okay? Then you can use your activation function will be changed. So neural network can be used in supervised, unsupervised, and the third category is, even we have a fourth category, but the third one is reinforcement learning. And we saw earlier the definition of this one. Reinforcement learning is what kind of learning? I'm just checking you. What kind of learning it is? Reward and penalty. That is sufficient. Okay. That is sufficient. If somebody will say reward and penalty, okay, hali hali. Yeah, khalas. It means that he knows that concept. So, so you can use neural network in supervised learning, unsupervised learning, and reinforcement learning. And if you will see the CLO, we are covering supervised learning techniques. So I will cover this neural network again in unsupervised also. And there the topic would be different. Okay, that would be some detailed neural network. Here we will go with the simple neural network, and which I'm sure that you already have studied before. Okay. So for example, when I will reach here, so this new artificial neural network, ANN or simply NNN is the same thing. Okay. And then Okay, feed forward. But this CNN, we will cover this CNN in unsupervised. This is a very much detailed model, okay? But we will cover this. And rest of the model. So if somebody is teaching you deep learning, okay, he must have to teach you all of the things here, okay? This is all neural network. These all names that you are seeing here is using neural network. And in deep learning, normally you start with the ANN, you go with the FN, CNN, DNN, RBM. So you study all these models in deep learning, nothing else. Coming back. So so the minimum form of a neural network is what? It is containing one hidden layer, not more than that. Minimum neural network is what? It is containing, okay, input. Input means the numbers are coming into it, and then those numbers will multiply with the weights, and then it will go to the hidden layer. And after the hidden layer, if you want to do some processing there, normally this multiplication is there, okay? When you multiply input with the weights, this is what you are doing in the hidden layer. And afterwards, then the value will go towards the activation function, which can be softmax, sigmoid, which is the for logistic regression, anyhow, and many other. We will see them. So the smallest unit of neural network, it will contain only one hidden layer. There was a time, I think in 2015 or 16, maybe, I was saying this to my students that if you have up to three layers, that is the neural network, okay? Three layers mean input layer, one hidden layer, and one output layer. But if you have more than that, you can call it deep learning, huh? That model will be included in the deep learning. So at that time, there was no concept of deep learning when I was in 2015, 16. That was only the machine then. So that's why. And sometime I said to my students that if you have maximally five layers, you can consider it as a machine learning model, okay? But then this new deep learning title came into our era, and then now you can say, okay, if we will go with um, that definition, then I can say that if you have something five or more layers in your model, then you will include it into deep learning. But that is not a definition that is professional. No, it is something technical. Huh? It is something technical. I have a word, but I don't know how to say it in English. Okay, because that is the word I have in my own language. Okay, so yeah, so maybe you will not understand. Maybe you will. Uh, I think you will understand anyhow. So you can say there are some other words, but I will say the easy words. This is something a desi tarika. Tarika is Arabic. Desi is something local, which is Pakistan and India. Okay, Pakistan, India, Bangladesh. You can say this. Desi is the word for those. For those people, yeah. This is the yeah. Tarika is Arabic word. Okay. Desi is des means country. Okay. Des mean country. And when I say desi, it is country method. Okay. English translation is country method. So anyhow, leave it. So, but this is specific only for that region, Pakistan, India, and maybe Bangladesh. Okay, but Pakistan, India, especially. So anyhow, uh, so the small minimum unit of neural network will contain only one hidden layer. And if you have some more than one, and if the network is having more than one hidden layers, then you can call it the model which is coming into the division of deep learning. Okay. So now moving next. So this is the mathematics we already seen. We already seen Z. Z is equal to W dot X plus B in logistic regression. And W dot X plus B is was for one input. When you apply it for the whole, then it is something sigma is equal to 1. You are multiplying weights with the input vectors. This X would be input vector. This W would be your weight vector. And then you are multiplying and summing those values, and finally you are adding your bias into it, and then you have your z value. So actually we started with this w dot x plus b, and then we already said this, that how we can predict a class y which is available in our data set, so that we can use the sigmoid function over this z, and we have this formula there in logistic regression. So I'm not saying anything new. We will use the same things. And then we have the sigmoid function like that, the positive values, the negative values, and here the values for the class Y, which you want to predict, but it is available in the system. Okay. When your system will predict it, it will become Y cap or Y hat. Huh? So anyhow, so this is the formula. When you will use it, it will have a curve like that. We already seen this curve. We already seen this curve. Huh? This is a curve for the sigmoid. So there is no need to do this question that it is familiar or not. Yes, we are familiar with it. We saw these things in the previous topic, logistic regression. So that's why moving next. Now, this is the smallest units displayed. Okay, minimum. So minimal neural network is displayed here in this picture, if you are seeing. If you will see, so this x1, x2, x3, this is the input, okay? Input variables, and these variables will contain numbers, okay? And then W1, W2, W3, this is what? This is weights. And these are the variables, but it will contain what? Numbers. And then what? And here you are summing them up. You are summing, but before that, you have to multiply it. But before that, you have to multiply it, and then you have to sum up all the products that you are getting here. The multiplication results that you are getting here, you have to sum them up. And then we are adding this biasness into it. And then what we are getting? We are getting Z value. And after that, we are applying sigmoid over it. And then we are saying that we are receiving A here. A is some activation function. This is the place to apply some activation function. This is also a activation function, sigmoid, okay? But this diagram is giving you an idea that after this summation, you will have the value Z. Value would be, Z would be variable. And when you apply sigmoid over this Z, then you will get what? You will get A. You will get what? A. Or you can directly say it Y. And A is what? A is the activation function. Activation function. This is its application. So this is what? The minimum diagram of the neural network. And it is containing only one hidden layer, which is encircled with, you can say encircled with this. By the way, this sigmoid, okay, normally in most of the diagram, you will see that this is the hidden layer. Okay, this is the hidden layer. Anyhow, so now in this example, we have this a vector with weights, then we have the value for the bias, and then we have the input value vector, which is containing three values. And y is equal to what? We have this equation. This equation is equal to this thing, 1 over 1 plus e minus w dot x plus b. And this is what? This is z. This is that previous equation of logistic regression. That's why I am saying it speedily and quickly. That's why I'm going through this stuff quickly, because this is what? The same logistic regression. And here we are putting the value, we are multiplying. We are multiplying this W and X1, W2, X2, W3, X3. From these, we are multiplying here. Here, multiplying, and then summing them up and adding this biasness into it. After evaluation, you will have this value. After evaluation, you will have this value for the Y. And now you can apply further something over it. If it is something greater than 0.5, you can convert it into 1. Otherwise, you can convert it into 0. And in this way, then you will have 1 and 0. The class is predicted finally, you can say. Anyhow, moving next. So this is what? This is again very much similar to that logistic regression. Huh? Nothing changed up to this point. Up to this point, no any change. It's the same story. Up to this point, it is the same story, which is we studied in logistic regression. Okay, now moving next. What are the different types of neural network that you will see in your whole life? So artificial neural network. Okay, if I will say neural network, or if somebody will say artificial neural network, it's the same thing. Okay, it's the same story. Okay, some people want to predict their words, or some people want to show their words in a bigger picture. So they normally say artificial neural network. Okay, ANN and NNN is the same thing. Okay, so, and if somebody will say NNN, it is modesty. If something will say ANN, maybe you want to impress or affect something, anyhow, leave it. So feed forward neural network. Okay, that would be neural network. And from its name, feed forward, we will see that it will go always in forward direction. It will not come back for updating its weight. So we will see when it will come. So, and these blue ones we will study in this course. Rest of the things we will not study in this course. That's why it is highlighted with blue color. Okay. But but CNN mostly used for graphics, for image analysis or something like that. And deconvolutional network, somebody, I also have heard somewhere it is deep neural network. Okay, so 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 this is DNN, restricted Boltzmann machine. Boltzmann is a German word. Okay, that's why I'm pronouncing it German. Boltzmann. Okay, I'm not saying Boltzmann. Okay. So this is anyhow recurrent neural network and so on. You can read them by yourself. Okay. So we will cover only these three, not the rest. Rest of the things you will cover in deep learning, inshallah. So okay, moving from this. So this is human neuron anatomy. Okay. And here you can see different parts, but I am interested only this part, which is dendroid and which is this axon. These dendroids are these all branches that you are seeing here. These can receive what signal in humans. In humans, these can receive signals, and then axon or axon, whatever you want to say it. This is that part. So what this axon will do, it will transmit your signals. And what is synopsis? Synopsis, if I will here, where these two neurons, this is one neuron up to this point, and this is another one, and they here they are connecting with each other. That connection, okay, that point on which these two neurons are connecting with each other, this is called synapse. So this is a junction for receiving and transmitting the. So one neuron is receiving, other is transmitting. So this is a point, and we are calling it a junction. Okay, moving next. So we have the same ideology here in the neural network or artificial neural network. And now it's again the same picture. You will see here, this is the input, x1, x2, xn, nothing else. We have seen this example before here, practical example. So this is limited example up to three inputs and three values in the three input values and three values in the weights. But here we are giving a general picture. And here you can see the input from x1 to xn. And then you have the weights from w1 to wn. And what is the next step? Multiplying and summation. Multiplying and summation. I don't know. Okay, I can make it bigger one. But now when I make it bigger, my pen is not working, okay, which I am using as a pen. So now it's a sigma is equal to 1 to n. Here we are multiplying. We already know that. We already know that. We don't. So we are multiplying these weights with the respective inputs here in this step. So you can call it transfer function. We are multiplying and adding. And then we can add biasness into it. Okay. And then after that, here you can apply some activation function here. Sigmoid is one example. Softmax is another example. And you will see soon after some slides, we will we will try to cover at least 8 9 different activation functions. So here you can apply some activation, and then you have this output at y. So this is diagrammatical illustration. Again, if you will see there, so now this is a little bit complicated. Little bit complicated. This is something when you have single neuron, huh? And this is something when you have multiple neurons. Okay. Anyhow, so this is input value from x1 to xn, and this neuron is connecting something with all, and this x2 is going towards the all. You have, for example, these three. This is the hidden layer which has these components. And what is the difference here? This input is going to all the components of the hidden layer. This is the only difference. And from after hidden layer, the values. So now you can apply some activation function here in the hidden layer, and you can also apply some activation function here at the end. So that's why it is depicted at two positions. This is not necessary that you can only apply the activation function only after the hidden layer. Like in logistic regression, you have the sigma at the end. It doesn't mean that you cannot apply some other activation function after the sigmoid or before the sigmoid. Similarly, in neural network, if you have the softmax, it doesn't mean that you cannot apply any activation function after it or before it. So that's why these two positions are displayed here, that you can use any activation function at these positions. So anyhow, so normally in artificial neural network, now we will not talk about the minimal component. It can be minimal, it can be more than one, huh? Neurons connecting with each other. So that's why. So then, but one thing is sure, that we will have the input vector, and then we will have the output, and then we will have the hidden layer. Then we will have the hidden layer. So this is something sure. So, and most of the time when we will talk about neural networks, we will represent our, this is the representation of our inputs, x1 to xn. This is the representation for weights. And this is the representation for weights. And we know that in artificial neural network, we will have one input layer. We will have one output layer, okay? One output layer. And then we can have a hidden layer. It can be one, it can be more than one. If it is more than one, then according to our previous statement, it will go into the category of deep learning. Huh? It will go into the category of deep learning. This is now, you can say, actually, I will say that, okay, you can say if it is more than one hidden layer is there, you can call it deep learning. This is what now we have in the literature. But in old times, even we have three hidden layers, we were not calling it the deep learning. We were calling it machine learning. Huh? So the other story is same. An input will come, you will have the weights, you have to multiply, then you have to sum, then you have to apply the activation function, and you are still in the hidden layers, huh? And then you will get the output layer. And in this way, this process will go on until you will reach at the last neuron, okay? If it is something mentioned, one neuron and then next neuron, then next neurons, the output of one neuron will become the input of other neuron. In this way, if you have multiple neurons in it. Now, here, this is just a diagram that something is going into it as a, so these, so banana, apple, ananas, and maybe this is orange. Huh? So these are images are going into this model. And here, so this is the input, and okay, this is the output, and whatever in between is what? The hidden layers, you can say, huh? The hidden layer. But if this is the input, and if you will specify that these are the weights, then everything else, then at least these two would be hidden layers, and this, sorry, this green one would be the hidden layers, and this orange one would be the activation function. Yeah. You must have to know what are the components of a neural network. Actually, the logic is. Logic is it is input, it is output, it is hidden layer, it is activation function. You must have to keep these four terms in your mind. So what is activation function? Now the question is, what is activation function? Activation function, if you will go into the definition of this activation function, it is something which will decide what is to be fired to the next neuron. Okay. So if it is only one, you have only one, you have a simple model with one neural network, then activation function would be something which will give you your final result, your output, huh? Which will give you your output. And if you have more than one neurons in your models, then the output of one neuron will become input to the other neuron, and then you can say activation function is something, is a component which will decide what to be given to the next neuron, huh? Okay, these are just diagrams, nothing else. So here we are representing that this x0, this is coming maybe from the previous neuron, this neuron, okay? From this neuron, this x0 is coming, and then you have this weight w0, you will multiply, then you will sum up, and then apply the activation function, and here you will have your output. This line, this green line is showing that this input is coming from here, okay? From previous neuron, okay? Just to clear what it is clearing, it is clearing the idea of this activation function, huh? Activation function normally divided into two categories. What are those? Linear and non-linear. Normally linear means straight line, huh? Something like that, which is starting from the lowest point and going straight forward in the upward direction like this. This is linear. This is the line for the linear equation. And then non-linear is something which can go in any direction, huh? For example, here the points are not like straight line, it is something like a curve. So when you have the shape like that, then it is called non-linear. And activation function is divided into these two categories, linear and non-linear. Now we will go into further detail of it. Okay. Yeah, this point is interesting point. If in your model you don't have activation function, okay, if, if you're in your model you don't have an activation function there, then the output that from your model, whatever the you will get, it would be what? Linear output, like this. Hmm? Like this. So this is an interesting point. So you must have to, if you don't have any activation function in your model, then you will get something like that. And this linear function has the less power than the non-linear. Okay. Now, if we want to understand, so that's why now we will go linear. We will not go into linear. We will go into this non-linear, because it has more efficient, or you can say it is something more valuable activation function. We will go into the non-linear category. So how we can understand the non-linear category? In non-linear category, we will have two concepts. The first concept is differential function. Differential function. This is again, you have, if you will convert it into lemma, if you will convert this word into lemma, you will get a difference, huh? So, or differ, or so differential function is would be some function which will give you the difference between two things, huh? So that's why it is, I mentioned here that this is something, a change in y with respect to change in x. This is, I mentioned here, with respect to this x and y axis on in the graph, okay? In the graph. If you will see, when you plot the graph of some model, and if you will see the change in y and also the change in x is also happening, in the data, then you can say that this is what? This is differential function, and it is like a slope, or it is like a derivative. Again, again that thing, huh? So anyhow, so you have to keep this thing in your mind. If the value of x and y is changing in the data, then it would be, or if you plot the data on a graph, and if you will see changes in y and x, then this is the property of differential function. Similarly, monotonic function. What is this? You will see if you plot the data on the graph, yeah, which means if you plot the function in the form of a graph, and if you will see entirely non-decreasing, or the word is or entirely non-increasing, so then it would be what? It would be monotonic function. So either decreasing or increasing, either decreasing or increasing. If you will see something, then it would be called, because now it is only one direction, either increasing, either decreasing. So keeping only one direction. So that's why the name is monotonic, from monotonicity. So monotonic normally means, okay, you have something unique in one direction. So let's see some important types of non-linear activation functions. The sigmoid we already know, the sigmoid we already know, and we are calling it that it is a differentiable function, because the you have the values, when the value of x is changing. If this is x, y is also changing. If x is 0, y is also changing, huh? If x is -4, y is also changing. X and values, if you will see this graph, huh? If, for example, if it's touching here, and the y is now here, and here, if 0 is touching here, now the y is also decreasing. So the change in x, if you change x, you will see the change in y. So this is differential property. Monotonic, which will have increasing or decreasing. When you have the word or, it means increasing can occur and also decreasing can also occur. And if both properties are there, that is also true for monotonic function, huh? If you have one, then that is good. That is according to the definition. But normally or you understand, or if both conditions are there, that is also or. This is what you have studied in computer science, huh? So 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 this function from this graph, you can say it is increasing, huh? And it is also has the decreasing trend in it. From the diagram, you can understand. So you can also call it monotonic. So it is sigmoid is what? It is differentiable function and it is monotonic. So that if you have these both properties, then you can call it non-linear activation function. And the other information you already know. So that the 0.5 is the threshold. If it is less than 0.5, we are considering it 0. Huh? And if it is greater than 0.5, we are considering what? 1. So I am not explaining these because you already know. And we used this activation function for what? Only binary classification. Okay. Only binary classification when two classes are involved. That's why 0.5, it is all the values less than 0.5 converted to 0, which means 0 is one class, and all the values higher than 0.5 is converted into 1. 1 means another class, which is predicted. So only two possibilities, 1 or 0. So that's why it is binary classification. Moving next, hyperbolic tangent function or tangent edge. So this green which you are seeing here is the tangent, and this red one is the sigmoid. Okay. Suppose previously you can say that this green one is more looking like a sigmoid according to that previous diagram, but the values here are changed. Okay. Here the values are changed. those values are going up to -8 and +8, and this is only -3, okay? So then the curve is short, okay? Then the curve is short. And here you have the y, here you have the x, sorry, here you have the x, and here you are applying the function over it, which is tangent function, which is what? Tangent function. And then you will get the values between -1 to 1, between -1 to 1. So if this, and here, this point, which is the median point, this is now, here it is 0, and also the y, you can also say the y is also 0. So it is, this tangent h is similar to that sigmoid, but its range is different. Its range is -1 to +1. And it has also the differentiable and monotonic property there. You can, even by looking at the curve, you can say, okay, the increasing and decreasing is there. Hmm? And if increasing decreasing is there, you can say, okay, if it is x, it is y is 0, and if x is 2, then the y is also increasing. So this is differential. So it is differentiable function and also monotonic. Both the properties are there. So that's why it is non-linear activation function. And you can use it for what? Again, two class problems, binary classification, binary classification. And you can use it in feed forward neural networks. Feed forward neural networks. Normally used in a feed forward neural networks. Moving next, softmax. So this is the equation for the softmax, that z is equal to 1 over 1 plus e raised power minus z is now finished. Huh? So now you have sigmoid of zi is e raised power zi divided by sigma j is equal to 1 to k e power zj. So now this is the equation. Okay. So we have, so here in this softmax, what is the range? If you will look over here, you will have the positive values, the negative values, and then you will have from 0 to, it is going, it is not up to 1.75. It is going more than that, okay? It is going more than that. So we will apply this. This is called exponent. Huh? So we will apply this standard exponential function to all the values, whatever the values we have here in the x, we will apply this exponent function or exponential function over it. And then we will normalize it by dividing the sum by all the exponentials. This is, here you are calculating the exponent of the z1, z2, z3. You can say, huh? For z1, you are calculating exponent for z1, then calculated for the x, z2, z3, and so on. And here you are summing up all the exponents, that you are getting here. This is the total sum of all the exponent, and this is what? Individual exponent, individual value of each exponent. So if my z are from z1 to zn, and then here if you will give, okay, this is z1, then it would become ez1 divided by, this is ezj, and it can be from 1 to n. If total z are k is equal to n, then you will add all those. That is what this is representing. So this is some kind of a average, huh? Some kind of a average. For example, if we have 10 members here, so this is Z1, this is Z2, and we are 10 over. So 1 over 10, 2 over 10, 3 over 10, 4 over 10. This is what it means, huh? This is what it means. This equation is saying this meaning to you. And that is what it is written here. So, yeah. And if after, when you are dividing it, 1 over 10, 2 over 10, 3 over 10, 4 over 10, 1 over 10, you will get some probability value, point maybe 1 or point 2, point 0.01. Huh? 2 over 10, you will get some point 2 maybe. 3 over 10, point 3 or something like that, or point 0.03. And finally, when you will add them up, whatever the results you are getting, finally, when you will add them up, all the values, you will get 1. You will get 1. So it means that whatever what values you are getting from this function, those values would be probability values, because it is what it is summing. When you sum them, it will give you 1. So you can consider those values probability values, and you can use this softmax for multi classification, not binary. If your classes are 5, 6, or 10, or whatever, you can use that one. For example, this previous example, it is orange, ananas, apple, or banana. Multi-classification. Multi-classification, because you want to predict. So more than two. It is not binary, it is multi-classification. Okay. And then if you will look over here, so previously it was some lower value, and then suddenly it is increasing. Suddenly it is increasing. So from this curve, from this, you can say, you can take any point here, and then you can draw the line which is a slope. So when there is a slope, then it means derivation is there. And it means you have different points there, okay? And it means that the change from that point to this point can happen. Or you can say if it is 4, then the y is, okay, for example, this one. If it is 2, where it is connecting? Here it is connecting. Then the y is here. So the change is there, huh? Change in y and change in x is there. So that's mainly. Yeah. So that's why we are saying it differential. And increasing is also there. And from here, decreasing is also there, but not like that. But not like that. So both properties are there here. It is not mentioned here that it is not monotonic. No, it is monotonic. But the prominent property is differentiable function. That is prominent. Otherwise, what is monotonic? Either increasing or decreasing. So increasing is there, and also it is starting from here, from 0, and then, okay, 0, and then it is increasing. So when something is increasing, that is monotonic. So that's why we are calling it non-linear activation function, because this is the non-linear activation normally have two properties, differentiable and monotonic. Okay. Now, rectified linear unit, ReLU, you already have, might be you have heard the name of this activation function also. ReLU, rectified linear. So linear, the name is linear. If you will focus on it, you will get some hint from it. Linear. So then you will see something linear in this, huh? So this line that you are seeing from here, if so this line from 0 and suddenly it is increasing like a linear equation, huh? It is moving like a linear equation. This is what we started with it. This is what? Linear line for linear equation. And that is the same property you are experiencing here. So, but before that, it was actually, but before that, for negative values, it is always 0. If you will look into the range of this ReLU function, here you have the positive values after 0, negative values, and then here you have positive values. But when you have the negative values, it is saying that when you have the negative values for this x, when you have the negative values, it will always remain at 0. Okay. If you will have your negative value in x, it will give you what? Output 0. And if you have positive value, then you will get some proper value from here. If you have, for example, 1, then you will get something from maybe 1 here. If you will have maybe, I don't know, maybe 4 or something, so then you will get something from here or whatever. So this relu function mostly used where it is we normally use it in CNN or other deep learning approaches. So then you can understand then this is something important function. Okay. If when you will see when you will go into the course of deep learning, you will see this activation function again and again. So in CNN or other deep learning models. Okay, I already have said this thing. If value is less than zero, if value is less than zero, then it becomes zero. And if value is equal to zero or higher, then you will get some number from here. Okay, then you will get some number, otherwise zero. Differential and monotonic both, because this is increase here. Change in y, change in x, change in x, change in y. That property is there, and monotonicity, which is increasing, or you can say decreasing. So, but it is increasing. Decreasing is something which starts from here and then it is going like that, huh? Then you can say it is decreasing. Hmm? Sorry? Yes, differentiable. Why? Because, for example, for negative values, you cannot differentiate, but after when you will have the positive values, then you can differentiate or not from this figure. For example, 0 to 5, when the value is 0, you will get 0. When the value is 5 for x, you will get what? Click over it, and then you will get almost 5 here, huh? Okay, I mean the slope of the function. Okay, after 0, it will be 1. Yeah. But at 0, there is no. Yeah, for negative values. That's why I guess it wouldn't be differentiable. I guess that I remember that the property of the differentiable functions that it could be like this. Should be like. It should be like the curve. Yeah. But here we have to find the property. That property is the curve is from here to here. Okay. You have to see the whole curve. Why you are focusing only this negative part? You have to focus. You also have to cover this part, which is the increasing part. And in this increasing part, you will see the change in x. You will experience the change in y also. For this part, it is true. But for this part, you are true. But we have to find the property. And if the property is there, then we can say it is differentiable. And we have this property there. The evidence is there. So due to this evidence, we are saying it is differentiable and also monotonic. And also monotonic. So, and the range of f, this activation function is from 0 to infinity. From 0 to infinity. And this is what whatever the issue is, we are mentioning it here. For the negative, you cannot map properly. It will give you some unstable value or node or whatever. This is mentioned. Okay, inshallah, I will start next in the next lecture. This is what I promised with Al-Jabiri, huh?